It's such a sunny day. If I manage to guide the light into my room, I can save on the electricity bills.
Do you want to grab the sunlight? That is simple. By applying the principles of refraction and reflection of light, sunlight can be guided indoors.
Guiding sunlight indoors? How do we do that?
We can use a solar lighting system. It collects sunlight during the daytime. Using the refraction and reflection of light, sunlight can be guided to an indoor area for lighting. It helps reduce the use of artificial lighting and hence reduce energy consumption and carbon emissions.
Dr. Tong, guess what? Sunlight can be taken indoors.
Taking sunlight indoors, like taking in knowledge from a book?
Think about it seriously. If I can guide sunlight into the room for lighting purposes, it will save a lot of energy.
Your idea sounds good. To achieve this, we have to know the properties of light. Do you know what they are?
I know. Light can be reflected.
Other than reflection, light is refracted when incident upon another medium. Under some conditions, when light leaves a medium, total internal reflection occurs.
It sounds quite complicated. What do they actually mean?
Let's do some experiments to understand these concepts.
Okay, let's go.
Sure.
What experiment shall we do now?
We will demonstrate the reflection and refraction of light, as well as total internal reflection. After understanding these phenomena, you will know how solar lighting systems guide sunlight indoors. As laser will be used, we must wear safety goggles to protect our eyes.
Okay.
Let's demonstrate reflection first. Here is a semicircular shaped transparent container containing tonic water. Tonic water glows when illuminated by a blue laser. You will see a clear path of the light beam. A plane mirror is fixed here. When the laser shines on the mirror, the light beam will be reflected. You can pay attention to the angle of incidence and the angle of reflection and learn how they are related. Let's begin.
Oh, the light beam seems to form an isosceles triangle.
Yes. The law of reflection tells us that when light is reflected, the angle of reflection is equal to the angle of incidence. As we see, both the angle of incidence and the angle of reflection are 20 degrees. Let's increase the angle of incidence to 50 degrees. The reflected and incident rays are still symmetrical. The angles are equal. Both angles are 50 degrees. Now the angle is increased to 70 degrees. The light rays are still symmetrical. The angle of incidence and the angle of reflection are equal.
I see. This is the reflection of light. How about refraction?
Let's take a look at another setup.
Okay. Dr. Tong, how does the setup show refraction?
The container is filled with tonic water. Let's shine a blue laser beam from the bottom. We can see how the light travels.
Why is the angle different after the light beam leaves the water?
This is known as refraction. Refraction means when light travels from one medium to another, the light path is bent. We just saw that the light beam bends outwards when it travels from water to air. On the contrary, the light beam bends inwards when it travels from air to water.
What is total internal reflection then?
Let's try to increase the angle of incidence. Now, we do not shine the light beam from the bottom, but from one side instead. The angle of incidence is increased. Let's see what happens.
Wow, that's amazing! Why does the light stay in the water?
When light travels from water to air at a large angle of incidence, the water surface will behave like a mirror and reflect all the light. So, the light beam will not enter the air. This is called total internal reflection.
Dr. Tong, how is total internal reflection applied in our daily life?
Hold this.
Why do you give me a fishing line?
Watch carefully.
Wow, how come the fishing line is glowing?
It is not a fishing line, but an optical fiber. I shine a laser beam from here into the optical fiber. Light is reflected many times inside. It travels through the entire fiber and reaches the other end with a little leakage. Therefore, we can transmit signals with optical fibers. Thanks to the invention of optical fibers, we have well-developed internet nowadays. It helps us transmit signals at high speed.
We've done so many experiments. How are they related to solar lighting systems?
Solar lighting systems make use of reflection and refraction to collect sunlight and guide the light from one place to another. The process usually involves many repeated reflections or total internal reflections. Now, we will do a series of experiments to illustrate the process.
Let's do it!
Okay.
Now I know the properties of light, including reflection, refraction, and total internal reflection. Dr. Tong, I still want to know, how do we bring sunlight indoors?
This experiment is the first step of a solar lighting system. That is the collection of light. It relies on refraction. We have two lenses here. One is a concave lens. The other is a convex lens. We will put these two lenses under a light source to see the images formed.
Okay.
Let's start with the convex lens. What do you see?
The light is concentrated in the center.
Yes. The light converges into the center and it looks bright. Let's try the concave lens. What do you see?
Not much difference, maybe a bit darker.
Right. The center becomes darker because the concave lens diverges light. It looks darker when the light gets diverged.
Dr. Tong, if I want to collect sunlight...
Yes? Which lens will you use?
The convex lens.
Exactly. We can also do a quantitative experiment. Here is a model house. Light can pass through this hole and enter the house. A smartphone is placed on a lift table inside the house. The smartphone is used as a light meter to measure the illuminance due to the light passing through this hole. We will test with 3 situations. The first situation is without placing any lens on the hole. The illuminance is measured. The convex lens is then put on the hole and then the concave lens. We compare the illuminance in these 3 situations.
Okay.
Let me get the smartphone ready. Okay, we are ready. The brightness at which light illuminates the surface is measured in the unit of lux. What is the illuminance if we did not put any lens on the hole? It is 21,000 lux. Now I put on the convex lens. It is 94,000 lux.
That's so bright.
Yes. Now I put on the concave lens. It's only 9,500 lux. That is 9,500 lux versus 94,000 lux.
What a great difference.
It gets much dimmer when light is diverged. It is much brighter when light is converged.
That means I can use a convex lens to bring sunlight from outdoors to indoors.
Apart from the convex lens, some solar lighting systems use diamond-shaped or polyhedron lenses to collect sunlight from different directions. There is another method where a concave mirror is used to collect sunlight.
Is the experiment done?
Not yet. This is just the first step. Now we have the next step.
What's that? Wow. How does this thing collect sunlight? Dr. Tong, your model's broken.
It's not broken. I divided it into half on purpose, so you can see its interior. A layer of silvery reflective coating is fixed inside. Light can be reflected many times and travel along the light guide to reach the place where lighting is needed.
It sounds quite complicated. Can you explain?
We have designed an experiment to show the effectiveness of a light guide. Here is the model house with a light guide fixed inside. Light is incident from here. For the purpose of this experiment, the smartphone is placed at the other end of the light guide. The reading is about 11,000 lux. I wonder if you remember which lens is better for light collection.
Convex lens.
Yes, we will put a convex lens here to see if it is improved. Let's see what happens. The illuminance becomes 14,000 lux.
It's much brighter.
Yes, it shows that the convex lens can collect light from different directions. Now we put on the concave lens. It becomes 8,600 lux.
It is lower.
The light gets diverged. The diverged light is not reflected along the light guide. Part of the light is lost.
What if there's no light guide?
We can try it out. Let's remove the lens and also the light guide. But the test is not fair because the smartphone is not directly under the light source. Let's move the smartphone in so that the light meter is located directly under the light source, right beneath the hole. Even in this situation, the illuminance is only 3,100 lux, much lower than the results with the light guide.
But the light guide is short. What if my house is big and has many rooms?
We make it short just for convenience in demonstrating the principle. In practice, the light guide can be made very long. It is because the place where sunlight is collected may be far away from where we need the light. For example, it may be easier to drill a hole here to collect sunlight. But the room that we want to light up may be far away. Then we need a long light guide to guide the light from the collector to the room.
The light guide seems very useful.
Indeed.
And we've finished the solar lighting system. I can take it home for use.
Hold on a minute. You have only got a light guide. It can direct light from the collector to the place we need it. But do you notice that the exit is very narrow? Think about it. Do you wish to shine your light on such a small area while other areas remain dark?
Of course not.
Exactly.
What should I do?
We need a light distributor, also called a diffuser.
A light distributor? What is a light distributor? What does it do? What can this little thing do?
It is useful. Let me show you. We use the same model house again. There's a hole in the middle that allows light to enter directly. Let's take a look inside the house. A frog is located at the center. It receives the most light as light shines directly. When you look at the pigs, they are at the corners. They receive less light. I put the smartphone upright here. The illuminance on the wall can be measured. I will put two different distributors here to examine the effects. One of them is transparent. Another one is frosted. Let's see the difference and figure out which one is better.
Okay.
We will start with no distributor and measure the illuminance.
Okay, light off.
It is about 46 lux. Let's try the transparent distributor now. We put it here. Look at the reading. It is 77 lux. The wall becomes brighter. The frog was the brightest before because it is at the center. Now, when the distributor is used, the pigs at the corners become brighter than before. Let's try the frosted distributor. Let's see. It becomes 289 lux.
Why is it so different?
See? After adding the distributor, the frog at the center becomes dimmer, while the pigs at the corners become brighter. It is the difference between the transparent and the frosted distributors. Why are the light distributors useful? When light enters the distributor, it gets dispersed due to reflection and scattering. All corners receive more light. If we use the transparent distributor, light is reflected or refracted on the surface and therefore scattered in different directions. But since it is transparent, reflection of light is less extensive. The effect is less significant. What is the benefit of using the frosted distributor. There are tiny uneven spots in the frosted distributor. Those uneven spots are effective in scattering light. That diffuses light in different directions. It makes the light more evenly distributed in the room. When the distributor is placed, it is like a lamp. It is very bright. The periphery of the room and even the pigs around the corners become brighter. It is not a new thing. It is widely used in our daily life. The lampshade is also frosted. Its purpose is also to distribute light in different directions, so that the room is illuminated evenly. In some developing countries, the living standard is lower. Electricity for lighting may not be affordable. People make a hole in the roof and place a bottle of water into the hole. Sunlight is then brought into the house and evenly distributed to every corner. Sometimes they may also add washing powder in it, because washing powder is full of tiny particles. The particles can scatter light. It has a similar effect as the distributor. The light is distributed more evenly.
It's like the frosted one. That's impressive.
After watching the experiments, now you know how solar lighting systems work. Let me show you the solar lighting system installed in the headquarters of EMSD. We are now on the rooftop of the headquarters. Look, these transparent domes are light collectors. Under each dome is a hollow tube. The inner wall is painted with reflective materials. Light keeps being reflected inside the tube until reaching the floor below. Sometimes the places right above may not be suitable for installing collectors. The light guides may be curved, like the model used in the experiment. Indeed, the size of a light guide is much larger in practice. This is the lighting device. It looks similar to an ordinary lamp. All of them distribute light more evenly by using diffusers. According to the statistics in 2020, about 10% of electricity consumption in Hong Kong is for lighting. Using direct or indirect sunlight for lighting purposes helps reduce the use of electricity generated by burning fossil fuels. While saving on electricity bills, carbon emissions can also be reduced.